Hello and welcome back as we continue to investigate how to design finite state machines and how to capture that design as Verilog. What we're going to do now is actually explicitly capture finite state machine designs as Verilog. What I'm going to do essentially is give you a coding template for the Moore machine and for variants thereof. The example I'm going to use is a simple set of drag racing lights. The idea is that a car goes up to the drag racing line. There's a set of lights that go through red, yellow and green. Of course, on green the car launches itself down the line. This example actually started as a traffic light controller, but I quickly found a traffic light controller was a bit too complex to fit the code onto one slide, so I reverted to this much simpler code. We're going to look at the Moore machine and Mealy machine alternatives for implementing these drag racing lights. Here's the Moore machine on the left. You recall the outputs are associated uniquely with the state. The outputs here are the lights themselves, red, yellow and green. So in state S0 we're red, S1 yellow, S2 green. The inputs associated with potential branches in a finite state machine. Of course, what a finite state machine allows you to do is go through a set of states in a controlled fashion, but in many different fashions depending on what the inputs actually are. So in this particular Moore machine, upon reset we go to state S0. Then there's two branches coming out of state S0. If car is 0, we take the first branch, staying in state S0. If car goes to 1, we take the second branch, going to state S1. That means on the next clock cycle after car goes to 1, we'll be in state S1. State S1, of course, the light changes to yellow. Then no matter what the input is, on the next clock cycle we go to state S2, where the light is green. And again, no matter what the input is, on the next clock cycle we go back to state S0, where the output is red. Of course, for this to work well, the clock cycle would have to be pretty low. On the right, we have the Mealy machine alternative. Recall in the Mealy machines, the outputs depend both on the inputs and on the current state. Thus, you draw the outputs on the branch vectors, not associated with the states. Again, when reset is asserted, we go to state S0. If we're in state S0 and we have no car, the light is red, and we still go back to state S0 on the next clock cycle. At any point, if car goes high, that is the car is ready, we immediately set yellow to high and go to state S1. Then one clock cycle after we reach state S1, no matter what the input is, we set green to high and go to state S2. One clock cycle after hitting state S2, we send red as high, go back to state S0, again, no matter what the input is. Of course, the Mealy machine will have different timing than the Moore machine. How is that timing different? Well, of course, the Mealy machine, the outputs will change one clock cycle earlier in response to car than in the Moore machine. So this is that Moore machine controller captured as in Verilog RTL. Recall the basic structure of Verilog RTL are that our registers are built in always at pos edge clock box, and our logic, if specified as a truth table, and that is what you would use to specify a finite state machine logic, that logic is captured in an always at block. Now, one thing we've done here in this particular code, and you'll do in all finite state machines, is combine the output logic with the next state logic. The reason for this is quite simple. Some small portion of this logic is essentially decoding the current state, since that is usually minimally encoded, and certainly minimally encoded here. So a little piece of logic there is decoding the current state, and a little piece of logic here is decoding that current state. if you build these logic blocks in separate case statements, that logic won't be shared. You'll be replicating that logic. If you combine output logic and next state logic into one case statement, then you can share that state decode logic that's implicitly there. So for that reason, to automatically get this shareable logic as shared logic, we combine both combinational logic blocks here into one logic block. Let's look at the coding for these two procedural blocks. Up here we have the coding for the state vector. Always at pos edge clock or neg edge reset. If reset is low, current state is S0, else current state equals next state. Of course, we use non-blocking assignment out of habit, though it doesn't make any difference here. What is this doing? Whenever reset goes low, no matter what clock is the reset is asynchronous, we go to current state. Otherwise, current state goes to next state, and next state is the output of the next state logic. Then we have the combined next state logic and output logic. Because is implementing a truth table, which I could sketch out here, but we can fairly quickly infer it from the behavior of the finite state machine, and that's frankly easier to do. Then it's going to be captured. This core of this logic procedural block is a case statement. So this is triggered whenever the inputs change. Here I said always at current state or car. Of course, I could have written always at start. Then what I do here is initialize or pre-default red, yellow, and green to 0. This saves coding later on, and you might recall I want to make sure that all the outputs here, red, yellow, green, and next state, are assigned no matter what combination of inputs exist. I have to do that to prevent latches, and here I'm doing that at least for red, yellow, and green to prevent latches for them. Then I have the case statement. The case statement is predicated on current state, which is the state vector. Then quite simply, all I do is look at what's happening around each state to write the code for it. In a Moore machine, I have to set the output. And then I have an if-else statement or case statement to determine what the next state is based on the possible transitions in the finite state diagram. This is why I didn't draw a truth table. It is easier and more natural simply to go from the finite state diagram to the actual coding. So here in state S0, red is 1. That's the output associated with the state. It's a Moore machine, so it's being associated with the state. Then I determine the branching to the next possible state, which is of course the state we'll take in the next clock cycle. If car is high, next state is S1, else next state is S0. State S1, again Moore machine, yellows, the outputs are associated with the state, yellow equals 1. Here there's only one possible branch out, and I take that straight away, so I just write next state equals S2. If I'm in state S2, then green is equal to 1, and I want to then transition one clock cycle later to state S0, so I'll just say next state equals S0. Here I have a default, next state equals S0. This is doing two things. This is preventing unintentional latches, because if I'm not, I want to make sure that next state is assigned for all possible combinations of inputs, and this ensures that. In addition, I'm producing fail-safe behavior. That is, if due to some noise event, this finite state machine gets into state S3, then it will on the next clock cycle, it will go to a valid state, state S0. You most already noticed up here that I used parameter to identify the states. I gave the states somewhat meaningful names. Remember, parameter is a bit like constant in C. It allows you to give meaningful names to vectors of numbers. So here I just said state S0, or S0 is 0, 0, S1 is 0, 1, S2 is 10 and S3 is 11. And of course the parameter is 2 bits wide. Of course, current state and next state are also both 2 bits wide. And red, yellow and green are 1 bit wide. And of course both of these are type reg because they're assigned in procedural blocks. The other thing you might notice here are these synopsis comments in some of the comments. Whenever you see synopsis in a comment, what you're doing is you're specifying a synopsis directive. There's a number of those that are available to you, including turning synthesis on and off. But here what we have is a set of synopsis directives that optionally allow you to choose to exercise particular finite state machine optimization routines available within synopsis. I am not going to go through those routines. If you're interested, you can read the tutorial on finite state machine coding and synthesis. It describes how to operate those routines. To me starting to teach that level of details, starting to get into synopsis training rather than sticking to fundamental principles in RTL-based design. So here we have synopsis and enum states associated with this parameter, and of course that's exactly what we're doing. We're enumerating out the 4 states that this state machine can reach. Similarly, we have the synopsis and enum states here associated with the input to the state vector and the output of the state vector. And then we explicitly identify the state vector, the output of the state register, with this synopsis state vector current state. So that's the output of the state register here. As I said, this would then allow you to say in the design compiler, after you've run the first compile, you could identify the state machine, ask to do some state machine optimization. What it does is reorder the state sequence to reduce the amount of combinational logic, and you could choose to run those routines. To do that, you need to know what the state vector is and what the states are, and this is how the information is passed to design compiler. We have another directive down here, synopsis full case parallel case. What this is doing is telling synthesis that this is a full case. That is, we have code for all the possible inputs, and you can see that here because we've got the S0, S1, S2 in the default. So it's a full case, and thus we shouldn't have unintentional latches. It's also a parallel case. What that means is we have no priority logic here. We know we have no priority logic because if we reordered the statement blocks here, we'd get the same result. That is, these are all parallel to each other, they're all independent of each other. You might recall with priority logic, the ordering of the possible matches actually matters. At first this might seem a bit redundant. Can't synopsis work this out for itself? And I'm sure it can in general. However, finite state machines can get quite large. This case statement for a real finite state machine could have 30, 50, 100 cases in it. That is 30, 50, 100 different states with quite complex next state logic and could run several pages of code. I believe, this isn't documented anywhere that I'm aware of, but I believe that this directive helps synopsis identify that this is still what we know it to be, that is a full case, no unintentional latches, and a parallel case which builds flatter non-priority logic. And of course, because we have to name vectors like next state and red, yellow, and green, this combinational logic cannot be bundled in with the sequential logic. Otherwise, next state and red, yellow, green become the outputs of logic, outputs of flip-flops if you assign them with always that pos edge clock event. So what I suggest you do is use this as a template for all your finite state machines. Right? You're going to have case S0, S1, S2, and so on. You're going to have parameter S0, S1, S2, and so on, identifying the state encoding. You're going to have a current state and next state. You have your next state assignment. And then one state at a time, you write out what's going on. From one machine, what the output is, then an if-else statement or a case statement describing the next state transition. And again, you can just do that directly by looking at the states. So this is what I suggest you do when you have to implement a finite state machine. Look at this page or the variants we're about to go through and use that as a template. Here's some discussion. I've written out some of the things that I've talked about in this slide and some previous slides. It is recommended that you try to code each finite state machine by itself in one module. The possible exception to this is a Mealy machine, because you might recall in a Mealy machine you have paths from the inputs to the outputs that don't go through a register. In Verilog, in the last set of Verilog notes, we talked about this as the unconstrained path problem. Synopsys requires that all paths be constrained by going through a register. So you might want to combine the Mealy machine with other logic to prevent unconstrained paths. Otherwise, you'll have to hand specify the delays on those paths. The reason why Synopsys recommends putting each finite state machine by itself is you need to do this if you're going to run the finite state machine optimization routines. As I just mentioned, the combinational logic and the sequential logic is separated into two procedural blocks. Whenever we want to name some of the signals that are coming out of combinational logic, it must be in a non-clocked block. Otherwise, you'll get registers. A brief question: is this reset synchronous or asynchronous? It's asynchronous because of the or neg edge reset statement. And note the use of Synopsys directives. Synopsys and anything with Synopsys written after it is a directive to design compiler or design analyzer. Here we have Synopsys and noon states and Synopsys state vector current state, telling Synopsys what the state vector is and what the state sequence is. This allows you to use the FSM optimization procedures. And full case is saying all the input combinations are covered. Parallel case, this is not priority logic. Now let's look at the Mealy alternative. In the Mealy alternative, we have to capture the behavior that the outputs are associated with the transitions rather than with the states. So let's look at this for state S0. Here we have if car yellow equals 1, next state equals S1. We've bundled the yellow equals 1 in with the state transition. If car is high, we're on this state transition, yellow goes high straight away, and we're going to next state. So the difference is in a milling machine, we have to bundle in the outputs with the state transition logic. Notice here, else red equals 1, next state equals S0, that is this branch here. Once we're in state S1, we just simply want to go to green and S2 on the next clock cycle. Once we're in state S2, we simply want to go to red and S0 on the next clock cycle. We're still essentially bundling this with the transitions. There's only one possible branch, so there's no if-else statement. Similarly, on the default, next state is S0 and go to red. So this is the Mealy machine alternative. Again, what we've done is put the inputs inside the if-else statements, if there's branch decisions, or brought the inputs one clock cycle ahead because they're associated with the branches. Again, I suggest you use this as a template if you're coding a Mealy machine. The other alternative that's worth looking at is one hot encoding. Let's say you designed the state machine using, say, a Moore machine on the previous page, and you found you couldn't meet the clock period. You're always getting timing unmet. Well, what can you do? Well, the first thing you might try is running the Synopsys finite state machine optimization processes. That reduces the size of the next state logic. If that doesn't work, then you're going to have to bite the bullet, increase the size of the state machine, and go to one hot encoding. And this will give you a dramatic improvement in clock period. because we parameterized the coding, all we have to do is change that parameterization and the state vector declarations in order to recode the machine as a one-hot alternative. That's the value of parameterization, or one of the values. So this is all we have to do. Now the state vector is 3 bits wide, and we change the coding for S0, S1 and S2 as being one of those bits is hot at any particular time. Since S3 was an illegal state, we don't produce a code for that. Why waste an extra flip-flop on an illegal state? So this is quite a very simple change if you need to go from a minimally encoded machine to a one-hot machine, because nothing else has to change. These are all the changes that are required in the template a couple of pages ago. So that brings us to the end of that particular module. We went through the coding styles. What I suggest you do is go to the quiz for that particular module, and then let's go on and finish off with controllers, a review of controllers and a little bit of review of what's going on in reset before finishing this particular module. Thank you very much.